Alright, back recorded. Alright, so guys, momentum. Oh, did I? Oh, I didn't have these covered up. And so momentum is what times what? Mass times velocity. You guys know on the AP page, these are the equations down in the bottom left corner, right? Bottom left corner. Alright, so guys, we're talking about vector values, which means, guys, if someone's going left and someone's going right, is that considered negative versus positive? Yeah, different signs. Okay. This is conserved during collisions. Guys, whenever you see a collision, you should already be thinking in terms of momentum. There might be some other situations too. Yesterday, you guys saw a closed system and open system as it pertained to energy. I remember energy was conserved in a closed system, or work could be done on or by the system for open. Right, you guys are writing this in your notes, right? Right, your notes. Now, what do you think it is in a momentum context? Another context could be in terms of forces. If there's a net external force that's considered an open system, if there isn't, it's a closed system. Oh, yeah. Yeah, there you go. All right, so just told you closed system. There you go. Momentum was conserved. The sum of momentum before the collision equals sum of momentum after the collision. Well, usually a collision. Versus if something's open, how is this one different? How are you guys gonna write open? Guys, this delta P right here, there's a term for it. It starts with an I. What's it called? Impulse. Guys, delta P, that could be an impulse. Right? Notice these are all momentum terms. Yesterday they were all energy terms. Right?
Ready for this?
Conservation momentum. Do you guys remember those collision carts you guys had? Hey, now, this is a really general collision. Here, go ahead. Right. What do you think goes in this gold box? Guys, go ahead. Right. What do you think goes in that gold box right there? This is a really general collision. I don't even know if those objects are going to stick together or bounce off each other, or like have to play a tennis ball for a half bounce off each other. But it doesn't matter, because regardless of what type of bounce it is, it's all right. What do you guys write in this gold box? There you go. That right there. Okay, let's write a numerical example. Let's do some math here. Let's do some math. Okay, so what if this guy is 2 kilograms? This guy is 3 kilograms. This guy is coming in at about 10 meters per second. This guy is coming in about -1 meter per second. You go, bam! You're gonna collide right there. And then what happens? No, guys, can you, based on what I've told you so far, if I told you nothing else, would you know exactly what happens after the collision?
Yeah.
No, because they might stick together, they might bounce off each other. I don't know. Okay? So I'll give you one more piece of information. Let's say I tell you guys that post collision. Okay. So we got 2 and 3 codes. Okay. Let's say this guy bounces back with 1 meter per second, and I'll call it negative because it's still up. Okay. This is 2 kg, this is 3 kg. Okay. And the question is, what's this other one doing? I'll call it B final. Let's just call it B final. Okay, so you guys go ahead and solve it. I'll solve it. Stay a step ahead of me. We'll give you guys a head start. Give you guys a head start right here. That's it. So you guys ready? Alright, do some algebra here. Hey.
I have a pact with one of my friends of either responded to.
Did you guys get the same thing I got? Oh, and guys, the fact that it's positive tells me this is moving which way? To the right, just like if you're going to the right. Now, there's one more thing I want to check. Oh, what did you say? Energy. Guys. If I do an energy check, if I look at mechanical energy, and we talk about kinetic energy, right? Kinetic energy. Okay. Can kinetic energy increase? No. If it does, I created an impossible scenario. Maybe this could run backwards in time. Okay. Is kinetic energy allowed to decrease?
Yeah.
Yes. Yeah. Can it stay the same?
Yeah.
If it stays the same, it's like the Newton-Cradle's ball. Boing, superconductor. Yeah, perfectly elastic. Yeah, it would be good. Right. So let's do a kinetic energy check. Or maybe I'll switch heat color here. Right. So I'm going to say sum of kinetic energy initial equals. Okay. Now, guys, what's the formula for kinetic energy? 1/2 mv squared. Okay. So I'll do 1/2, and then I got 2 kilograms going at 10 meters per second. Square that. Okay. Plus, I got 1/2, and then this mass is 3 kilograms, and then, well, -1 meter per second. If I square that, it's still positive, right? Okay, so can I just say 1 squared? 1/2 mv squared. Okay. So I'll get at 101.5. Now that's the number on my calculator. Does that number have units? Joules! Yeah! Guys, that's joules. That's 101 joules. 101 joules. Okay. Let's do sum of kinetic energy post-collision. So final. Okay, so now I'm looking down here at these numbers. So I'll do 1/2. No, the masses are the same as before. 2 kilograms, but that's going at 1 meter per second and square it. Okay, plus 1/2. The other guy's 3 kilograms. Going at, we came up with 6.3 something meters per second. Square that. I'm getting 61.17 joules. So is this a plausible scenario? Could this have happened? Yeah. Okay, so momentum is conserved. If you account for kinetic energy, there's a decrease, which is perfectly fine. Yeah, looks like a realistic scenario. All right, you guys ready to go back to PowerPoint? Right here. Ooh. Guys, how about this? What if they stick together? It's a really similar looking equation, but it's a little different. Hey, go ahead and write. What do you think goes in that gold box? You have 2 objects collide and stick together. And you're going to have to solve one of these on the upcoming AP exam. They got to fit in one of these questions. They do about every year. So if you know this, you are getting yourself a point right now. All right, did you guys come up with? Oh, okay. So it starts out the same. Okay, but how does it finish differently?
Same velocity, but
Yeah. It makes one giant mass moving at common final velocity. Is that what you guys just wrote? Ooh, let's go back to. Let's go back to this example. Let's do that. Let's say these objects actually stick together. Here, guys, beat me to the answer. These objects stick together. What's the final velocity? I'm giving you guys a head start. Beat me to the answer. Who's gonna win? I won. Oh, but somebody won? Who won? What'd you get?
3.4.
All right. We got a candidate answer. 3.4. We're gonna find out. Oh yeah. What'd you get?
17/5.
17/5. What is 17/5? Well, that's the same thing. All right. So, I got 2 points on this. So let's go 2 by 10 plus 3 by -1.
Yeah.
Kilogram meter per second. Kilogram meter per second. Actually, we did this before, didn't we? This comes out to 17. That's equal to 2 plus 3. Those are kilograms. Big final. 5.
So you can just put it on your hands.
So, wait, 17/5? Yeah. Okay. 17/5 meters per second, or 3.4 meters per second. Alright, so Austin and Nathaniel. Ding ding. Winners. Everybody else being a winner? Oh, and here guys, before the first example we did, I didn't have to do a kinetic energy check because I could have here guys, what if what if I went way back? Let's go back in time. Like 1985. Where what if I made this number like -11 meters per second? Do you think it could have come up with junk numbers where I accidentally make an impossible collision? Yeah. So if you guys teach physics one day, make sure that whatever collisions come up with for like quiz or whatever, make sure it's actually realistic. Okay. But what about this one? Do I have to do a check, or am I guaranteed that this is always going to be okay? Okay. This one's always going to be okay. If we can do a kinetic energy check, kinetic energy will go down. Okay. Here, let's do this. Let's do 1/2. We have a combined mass of 5 kilograms. Let's go at 3.4 meters per second, and I square that. Okay. Now we're down to 28.9 joules of kinetic energy. So K final, 28.9 joules. I think that's as small as you can get on the kinetic energy. So they stick together.
What is it?
All right. Opposite end of the spectrum, perfectly elastic. Is that like Newton's cradle? Newton's cradle? You guys in auditory? Guys, you hear that? Clap, 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 clap. So what are the two conditions? What and also what? Momentum's conserved. Boom, boom. Oh, whoops. And kinetic energy is also conserved. For this very special kind of collision, it's just super bouncy, perfectly elastic. Okay. Now there's a solution to the system. It goes like this. If you got extra space in your mind, you could memorize that. But okay. There's maybe a 50-50 chance that some kind of elastic collision even shows up at all anywhere on the exam. And if it does, it's usually something where if it was a multiple choice question, you could run each of these. You could go through the multiple choice answers. Say, does A work? Does B work? Does C work? Until you finally find one that actually works where kinetic energy is conserved and so on. Okay. If it's a like a free response context, then it might be part of a bigger question where like, oh, there's a perfectly elastic collision, and you recognize that, oh, okay, the masses are the same, therefore, like all the momentum's transferred, whatever. Okay. All right, so let's look at there. If you go to college, they will probably actually have you solve this whole thing out. So hold on to these notes for college. This would be that. All right, types of collision. Oh, yeah. Pause this. Phone call. All right, we're back. We're back. All right, so here we have a spectrum of collisions: perfectly bouncy, perfectly elastic, something in general, and perfectly inelastic, where they stick together. Right? And then what's this down here? The fourth one, an explosion. Hey, isn't that kind of like a backwards collision? Collision in reverse. Right. All right, so guys, what can you say about momentum for this first one? It's momentum's conserved in general, right? In general. Okay. What about perfectly inelastic? Is momentum conserved? Yep. What about for an explosion? Guys, look up here. For an explosion, is momentum conserved? Raise your hand if you think it is. Oh yeah, my winners. Oh yeah, momentum conserved. Now, what if we switch over and look at energy? When were we just doing that? I was doing that all in pink ink. Kinetic energy. Guys, perfectly elastic. What can you say about kinetic energy? Also conserved. Right? In general, what happens to kinetic energy? Yeah, it usually decreases, unless of course it's perfectly elastic. Right? And anytime the objects stick together, what can you definitely say about kinetic energy? Yeah, it definitely decreases. What about an explosion? Okay. And of course that energy came from somewhere like the gunpowder or whatever. Okay. Or if you throw a ball. If you throw a ball, maybe the energy came from your muscles. Corn flakes. Ooh, you guys remember collision carts? You guys have lab? Okay, a little bit different lab. Are they stuck together? Guess with the magnets. Okay. Oh, look who it is! Ballistic pendulum. So guys, here's the classic question. A bullet is fired at some speed. What speed? Well, that is the question. You guys see, maybe there's like a whole process and it leads up to being able to answer that. What's the firing speed of the bullet? Okay. And normally you're given the mass of the bullet, the mass of this block. Usually you have the bullet embedded in the block, although there's variations on that. Okay. And there's some resulting height change. Okay. Now, do you guys remember from yesterday? Could you solve the height change in terms of this L and this theta? Right? Okay. Yeah, you ideally should be able to do that. Right. But let's put that aside just for a moment here. Let's say you're given the height change. Is that okay? Oftentimes AP will just say, you know what, this is complicated enough already. We'll just say this height change is like 17 centimeters or whatever. Okay. Guys, go ahead. We're going to start with conservation of energy, and then do conservation of momentum. And there's some process where you can ultimately find what is the firing speed of the bullet. Okay, so go ahead, give you guys at least a minute or two here. See if you can solve that in terms of variables. This good critical thinking right here. It's right in line with pre-response question level
I wrote
difficulty.
energy initial equals energy initial. Very, very. You're right.
Why did I put energy first and then momentum? Right, you're actually solving this backward in time, like chronologically. Okay. So I think the last thing that happened is that whole pendulum swing up to some height change. But before that, the bullet embedded in the block. Okay, so the swinging up motion, that sounds like conservation of energy, like from yesterday, hey. And that bullet embedding in the block, oh, okay, that sounds like a collision, like momentum. Yeah, you're trying to find the firing speed of the bullet based on the mass of the bullet, the mass of the block, the height change during that swing. And what do you think this would look like if you took this to the moon? Guys, if you took this to the moon, would it swing up to the exact same height?
Yeah.
Are you sure about that?
No, pretty sure.
Huh. Because what if you're in deep space? What if you're in deep space and there's no gravity at all? And you fire it. What does it do? It's going to start flying around in a circle. Right, now let's go back to the moon. Really weak gravity on the moon. Do you think the height change would probably be greater than on Earth? Right, then you go to Earth where the gravity is turned up. Okay. So I think gravity field is going to be part of the answer. That's what I'm trying to get at. Somewhere in there. Okay, so what is the firing speed of the bullet based on little m, big M, H, and I think gravity field is going to be in there too. Alright, let's see how you got doing here. Guys, everybody make believe that you're doing a free response question right now, where this might be worth 3 or 4 points or more. And even if you don't think you can get the whole thing, maybe you can pick up a point here, a point there. You say, well, I know at least this would have to be true, so you jot that down. Okay, well, you know what else I think would have to be true? You jot that down. Or you know it, you picked up 3 of the 4 points. Yeah, I think Lily got it. Got at least one winner. Ooh. Some of you guys got some steps. You're working toward it.
So we just is this gonna be the
Alright, who else think they got it? I didn't miss anybody, did I? Did I miss anybody?
you're probably like
Alright.
all wrong, but he's
Alright, hey guys, you ready for this? Guys, definitely you taking notes because you should know how to do this. You should know how to do this. Right? So yeah, I'm solving this like reverse chronologically. I'm starting with okay, the last thing that happens is it swings up to some height. Okay, so if it swings up to some height, this is turning from what type of energy to what type of energy? What type of does it have down here when it's moving really fast but it has no height? That's called kinetic. And when it moves up to some maximum height but it's not moving for a moment, it has what type of energy? Potential. Right. So something about 1/2 mv squared turns into mgh. Okay. And remember, this is all post collision. So we're talking about the bullet and the block together. But even if you forgot that detail, does that mass cancel out anyway? These 2 m's and those 2 m's cancel out anyway. Okay, so that's at least a true statement. Is everybody okay with that's a true puzzle piece on the board? It's okay? Okay. But where is this kind of going? You're kind of solving for which of those variables at this point? Yeah, guys, this V right here. And guys, look up here. So you know, you have to think really deeply about what these mean, what's going on. Is this V right here the firing speed of the bullet? Yes or no? You're right, it is not. It is not. What is this V? What does this V represent? Final velocity of what? Yeah, okay, yeah, after the collision. So after the bullet embeds in the block, this is the post-collision velocity, as in, well, post-collision, right?
Yes, it is routine.
But before it actually swings up to whatever height. Okay, and no surprise at square root 2gh. Maybe you could have been looking for that, right? Say, oh wait, I remember this from yesterday. It's got to be square root 2gh, right? Okay. Right now, let's go over to what happened before that, which is that there was some collision here. Hey guys, what was the source of all the momentum? The bullet, mass bullet times velocity bullet, and after it embeds in the block. What kind of collision is that called? Perfectly inelastic, which we just covered a couple slides back. So what does that look like?
Yeah.
Did you guys come up with that right there?
Yeah, I did.
Right there?
Then I solved.
Right. Here's the source of momentum. Right. And here's where it goes. Objects stick together. Right. Hey, is this V and this V? Is that the same thing? Yeah, because whatever post-collision velocity that was, that led to it swing up to whatever height. Look at that. All right, and finally, you're just one step away. It's just divide down. Just like that. There you go.
That's what I did. I just didn't. I just
Yeah.
something. I was. For the easy part.
All right, you guys give it that whole thing. Yeah, question right there. I almost forgot I put this on here. Recall that. You guys remember this from yesterday? Maybe I should ask you guys to write that too. Guys, could you get this in terms of L and theta?
Oh god.
Now, I'm thinking in terms of what AP might ask. If AP asks you this specifically, they'll probably narrow it down a little bit. It's like, okay, this is complicated enough. Okay. Because if you go to college, there's a good chance that in college physics you'll have to actually solve this in terms of L and theta. All you do is just sub this in for that H. Same thing. Ooh, impulse is equal to what? Which is also equal to what? Guys, what's our two perspectives on this impulse? What, or what? Yeah, here, I'm giving everybody a chance to write that in their notes. What do you think it is before I flash up the answer? It could be what times what, or what times what. Here, somebody guys tell me the answer. It said it could be m delta v. So mass times change velocity. This is assuming the mass doesn't change, which is usually the case. So you have like an assembly line of whatever. And an average force times time. And that matches to this graph right here. Hey, look, it is a force versus time graph. Guys, when you take the AP exam just a few weeks from now, are you guys going to see some force versus time graphs? Yep, they're going to show up, like guaranteed. And whenever you see a force versus time graph, the first thing you should start thinking of is there's something about momentum, change of momentum, impulse, which is what property of that graph? Area under the curve. Right? Now, oftentimes these look like triangle shapes. They rise and fall, like this ball slow motion is being hit by the bat. Right? Or you can simplify it. You can say, well, instead of a triangle shape, I could take the average force, which would be like halfway down, and make this a rectangle shape. Okay, so is this rectangle and this triangle, do they have the same area? Yeah. Right, let's do a calculation on this. Right, you guys ready? Let's say I got a ball coming in. It's gonna be hit by this bat. It's like pow. Say the ball comes in at okay.
At the same speed as
Let's use a baseball. 0.15 kg.
That's the right.
Let's say it's coming in at 30 meters per second. Let's say that the average
ball bat
net force on the ball from the bat is 500 newtons, and that lasts for 0.02 seconds. Okay. What I want to know is how fast is the ball flying towards the outfield. Call it V final. Case off for V final. Don't know 100% how realistic these numbers are going to be, but we're going to find out. Alright, give you guys a head start here. Alright, you guys got a good head start? Guys ready for me to catch up to you? All right. The way I wrote the numbers, there's a little trick in here. Once you guys caught it before I pointed it out. Okay. Guys, what I do, V final minus V initial. What V initial should I put here? Okay, yeah, I like the idea of going negative 30. Okay. Guys, if you do regular 30, see, the problem is this. Guys, this force has a direction, and these velocities also have directions. When I say the force is 500 newtons, that's from the bat on the ball pointed which way? To the what? To the right. On my paper, towards the outfield, to the right. Okay. Guys, if I'm being consistent with the numbers, this initial velocity should really be negative, shouldn't it? And now yesterday we didn't have to worry about that because energy was scalars. But today momentum is a vector. So this should really be negative 30, shouldn't it? So I'm peeking right here, negative. And you have to do that in the math, otherwise you'll get the wrong answer. So I'm really subtracting negative 30 meters per second right there. Yes.
What'd you guys
Think about directions.
90s?
All right. 500.2. Okay, so I'll do that right there. Divide by 0.15 at negative 30. Okay, I got an answer. Are you guys getting 36.67? Do you guys get that?
Yeah.
Okay.
Yeah, sure.
Let me double check my answer. 0.15.
Miles per hour.
Per hour.
I legit.
Yes, that's right.
Yes. Anyways.
All right. There we go. All right, you guys can solve impulse. You guys good with impulse? How about inelastic, where the bullet collides and sticks to the bowling ball, versus elastic, where this bouncing ball, the bowling bounces off. What if both the bullet and the bounce ball have the same mass and they come in the same velocity, yada yada? Okay. Guys, which one of these gets the bowling ball rolling faster? Here, let me see. Show hands. It's either first or second. Show hands. How many of you guys say the first scenario gets it rolling faster? Who says the second scenario gets it rolling faster? Yeah. Right. Gotta be the second case. Right. Yeah, if it bounces backward, you can transfer up to twice the momentum into that bowling ball. Yeah. Yeah, that's a good point too. Yeah, if it sticks to it, that also increases the mass. Yeah, that's another little detail. That's also true. Yeah. Further next point. Ooh, ball bounces off the ball. Guys, if this ball is headed towards the ball at 10 meters per second, it bounces off at 7 meters per second. The other direction. Who can tell me what's the change in velocity of that ball? 17. 17. It's 17. 17 meters per second. Nobody said 3, right? You guys said 17?
Yeah, nobody said.
Nobody said 3. Nobody
said the triple.
And guys, this average net force from the ball on the ball. Is this just the impulse formula rearranged? Or is this just Newton's second law broken down a little bit? Yeah. Guys, impulse and Newton's second law are just one step away from each other. How about this? Guys, if you throw this ball, the boing bounces off. There was definitely a force from the wall on the ball, right? Because it changed the motion of the ball. Was there a force from the ball on the wall? Guys, is there a force from the ball also on the wall? Yeah, but the wall doesn't move, right? It's grounded in the earth. So which force was bigger, the force on the ball or the force on the wall? Same force. Does that sound like Newton's third law? Same force. It's the same force. Right? Ooh, can you go two-dimensional? Guys, let's play off this angle here. Guys, go ahead and write, what do you think of those boxes? Go ahead and fill in those boxes. Solve the one-dimensional case. Just the ball bounces straight back. But what about if you have a significant angle there? Notice I'm doing the angle relative to the wall. You could also do the angle relative to the normal, which would, just the sine and the cosine would swap places. Okay, so whatever angle you're given, make sure you make sure all your sines and cosines align to that particular angle. This looks like the angle relative to the wall. Is that yellow box the same as it was the last slide? And what'd you guys write here? What over what? Yeah, m delta b over delta t. Okay. Now, since momentum is a vector, you do have to consider x-axis and y-axis. Now, if I'm looking at along the y-axis, so like parallel to the wall, because if I'm just watching the ball go parallel, parallel, parallel to the wall, does it change after the collision? No, this is a very special collision. It's perfectly elastic, frictionless wall. Yeah, guys, if I'm just looking at the y, the y coordinate of the ball, I never even know when the collision happened. It's just going, 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 going. But in the x direction, it completely reverses direction, doesn't it? In the x direction. So, which direction is the force? The force is only in the what direction? In the x direction. Okay. Now, if you go to college and make this more complicated, they might put some friction with the wall. And could you say friction force is going to be parallel to the wall? You can do some Pythagorean to find the net force, yada yada, right? But this is probably as deep as AP might go. Okay. So what actually goes right here? Again, since we have a simplified scenario with perfectly elastic and so on. Okay. Guys, can this V naught sine theta and this VF sine theta, do you guys think that V naught and VF are the same for perfectly elastic? Yeah, if it comes in at like 11 meters per second, it also bounces off at 11 meters per second or whatever. Okay. All right, so with all that in mind, what do you guys put in that gold box? Thanks. You guys wrote something kind of like that. You guys write that? Okay, because here, guys, the ball's coming in at directly towards the ball at some V sine theta. Is that true? Some V sine theta? Right. Now, what if the ball stuck to the wall? Stuck to the wall. Wouldn't it go from that speed to 0? Right. And then you would just have m times V sine theta all over t. I just don't. But if it bounces back, boing, now it's leaving at the same speed but opposite direction. Is that where that 2 comes from? Is that why it's 2 right there? Right? Because we have this special scenario, it's perfectly elastic, there's no friction. Yeah. Okay?
No.
Right, so kind of a special scenario there. But you can see the general principles. Ooh, what if you did see a collision in 2 dimensions? AP usually doesn't get this deep quite. Right? But if you go to college, you might see like a car crash or billiards or something like that. Can you guys do in the x direction and also separately in the y direction, momentum's conserved, and do a system of equations? Right, so you could do that in principle. You won't see that on the AP exam, but all right. I got a trio posters that go together here that will show up in some conceptual way on the AP exam. So, because we're deep space, we got these asteroids boing colliding. Maybe they bounce off each other like here. Maybe they stick to each other like here. Maybe it's all in 1 dimension. Maybe it's a 2-dimensional collision. Maybe it's a 3-dimensional collision. What can you say about the center mass for all those situations? Yeah, the center mass. If you just focus on the center mass, not the objects themselves, but the center mass, would you ever even know where the collision happens? No, you have no idea. Center mass is unaffected. Right. Ooh, do you guys remember Magic School Bus clip? You guys remember that frictionless baseball field? Pitcher throws the ball one way, scoots back towards second base the other way. Okay. Now, if you know the mass of the ball and the speed of the ball relative to the ground, and you know the mass of the pitcher, can you solve for the speed of the pitcher? Okay. Here, go ahead. Right, what do you think goes in that gold box right there? The derivation where you can solve for what's the speed of the pitcher sliding back towards second base. Or actually, I think on this one I put something about say an ice skater. Yeah, guys, if you ever open up a physics textbook and says something about an ice skater or an icing surface, they're getting rid of the friction. Okay, so there's no friction. Say friction is negligible. There's no friction. All right, did you guys write momentum is conserved?
Yeah.
Is this kind of like a reverse collision? Reverse collision? Like if you filmed this and ran it in reverse, it would look like a collision, wouldn't it? Yeah, just a collision in reverse. Right? You could say it's an explosion. You do that. Okay. Now, if the pitcher starts on the mound with at rest with the ball, or in this case, maybe a snowball, whatever, okay, there's 0 momentum in the system. That means there's only ever 0 momentum in the system because it's a closed system. Closed system. Right. All right, so the ball going one way and the skater going the other way, the momentum will have to cancel out. There you go. Okay. Then if you know 3 of those 4 variables, you solve the 4. Right, you guys can do that. All right. Okay, so if I told you the mass of the ball was like 1 kilogram and the skater was like 50 kilograms, and the ball is going like 30 meters per second. It's off for a B skater. Ooh, how about a grenade explodes midair? Oh, look at all these grenade parts. There's like 100 grenade parts all going different directions. What can you say about the center of mass? Yeah, unaffected by explosion, stays the same. Yeah. Okay. So the center mass of all grenade parts lands exactly as if it had never exploded at all. Okay. I've seen AP ask questions in the past, like usually they just break it into two pieces. They say, "Oh, maybe the grenade breaks exactly in half, and one piece lands like 10 meters ahead, while the other piece would have to land 10 meters behind." Yeah, that's all. Right? Like that. Okay, this is a little deeper, but I've seen AP award points for students who know this. Guys, kinetic energy. What's the formula for kinetic energy? 1/2 mv², and for momentum, it's what? Mass velocity. Momentum is mass times velocity, right? That's the same ingredients, right? So if you're working with the same ingredients, if you know what mass and velocity are, there could be this connection. And it goes like this: the kinetic energy of a point mass is its momentum squared divided by twice its mass. Right, here's a derivation to show that. Okay. And then eventually when we get to rotational mechanics, like if a ball is rolling across the floor, here's the rotational version of that. Okay. Right. You guys good with that? How bouncy is a collision? I've never seen AP ask this question, so kind of go through this. It was a good lab, right? It's a good lab, but AP's not going to ask that, so skip through. Yeah. All right, I think that's all I got right there. Yeah.